We have to name compounds a little bit differently if they are molecular compounds, not ionic. We already talked about how to recognize molecular compounds. If the compound is made of all nonmetals, then there's nothing that can form a cation. So for example, phosphorus, when it forms an ion, forms a phosphorus with a -3 charge. Chlorine, when it forms an ion, forms chloride with a -1 charge. So if we put together 5 chloride ions and 1 phosphorus ion, the total charge would be -8. We would not be able to form a neutral compound like that. So these do not form ions in order to form this compound. Instead of forming a set of 8 electrons, the octet rule, by getting a charge, what the phosphorus and the chlorine do are to share the electrons, which we will look at in Lewis structures in the next section. But anyway, these are not forming ions, and so we're going to name them differently to show that they are not an ionic compound. Carbon over here with oxygen, I just wanted to point out, carbon usually does not form an ion because carbon has 4 valence electrons. Oxygen has 6 valence electrons, so it can form an ion with a -2 charge to complete the octet. Carbon has 4 valence electrons, so to complete an octet, it would have to either lose those 4 electrons or gain 4 electrons. That is too much for a small element like carbon, and so carbon usually does not form ions. So carbon gets its complete octet not by forming an ion, but by sharing electrons and forming covalent bonds with other atoms, which is part of what makes it so great and very versatile as far as forming really interesting compounds. So because these molecular compounds do not form using charges, we cannot use charges to figure out how many of each element we have. For example, if we have an ionic compound like magnesium bromide, we can use these charges that magnesium forms a +2 charge and bromine forms a -1 charge to figure out what the formula is, that it's 2 bromines and 1 magnesium in magnesium bromide. So we use those charges to figure out how many there are. We can't do that with a molecular compound. Instead, we have to use these prefixes to tell us how many of each element we have in there. And these are the prefixes that we are going to use. If there's 1 of the element, we can call it mono, 2 is di, 3 is tri, then tetra, penta, hexa, and so forth. The prefix mono is optional, so it can be omitted if you don't see a prefix. It means there's only 1 of that thing. It is especially always omitted if it's at the beginning of the word, because we don't want all molecular compound names to start with the prefix mono. That would be monotonous. So we omit the prefix mono if there is 1 of the first element in the formula, and if there's 1 of the other elements in the formula, then that would be optional. The other prefixes are not optional. We have to use them. I think this will make more sense when we actually try some examples. Let's go ahead and do that. This formula has 1 phosphorus and 5 chlorines. Although if it's the second element, we are still going to use the IDE ending. Even though it's not a negatively charged chlorine, we are still going to call it chloride. So phosphorus, there's only 1. We omit the prefix mono and just call it phosphorus. And then for the second element, chloride, there are 5 of them, and so we're going to use that prefix penta. So the name of this compound would be phosphorus pentachloride. This one we have 1 carbon. We're going to omit mono and just call it carbon. And then there's 1 oxygen. This time I'll go ahead and put the prefix just because a lot of people are familiar with the name carbon monoxide. Instead of monooxide and having a double O, monoxide is just spelled with 1 O. So the prefix mono and the word oxide kind of share that letter O. So carbon monoxide is the name of this compound. I suppose you could also call it carbon oxide, but I think that's less common in this particular case. This one is called carbon, again with one carbon, and there are 4 bromines, so we are going to call this tetra, and then bromide. We'll change bromine to bromide. This one, there's not just one nitrogen, there are 2 nitrogens, so we are going to use the prefix for the nitrogen. We'll call that dinitrogen, and then we can either call this dinitrogen monoxide or dinitrogen oxide. Okay, so going the other direction, the first element, sulfur, does not have a prefix, so we know there must be just one of them. There's one sulfur. And then the fluoride has a prefix, hexa meaning 6, so there are 6 of the fluorine atoms. This one we have 1 carbon, and this time we have 2 oxygens. So CO2, carbon dioxide. This one we have 2 borons and 3 oxygens. And this time we have 2 nitrogens and tetra 4 of the oxygen. So the good part with these prefixes is that it makes things very clear. The difficult part is that once students learn the prefixes, they want to use them on all the compounds. And a lot of times we are going to have ionic compounds. You'll notice that we did all this work already on naming ionic compounds before we learned the prefixes. That's because these prefixes are not used to name ionic compounds. So just be careful that you don't start throwing these prefixes all over everywhere when you try to name things, because that would not be correct. Make sure that you have a molecular compound before you go using these prefixes. I mentioned before that acids have their own way of being named. Personally, I think that it's just easiest to memorize a bunch of acid names, but there is a little bit of a pattern. I figured I'd show you in case that helps. If you have an acid that only has hydrogen and another element, so there is no element X, this just represents a different element, not hydrogen. All of these formulas of acids, you'll notice, start with hydrogen, at least one hydrogen, sometimes more, as the beginning of the formula, because they are hydrogen ion donors, and that's what makes them acids. So if that acid is just a hydrogen and one other element, then you would call it hydro blank ic acid. In this particular case, the blank is filled by chlor because it comes from chlorine. So hydrochloric acid would be the name of this compound. And then similarly, hydrobromic acid would be hydrogen ion and bromide ion. So HBr would be the formula for hydrobromic acid. These other acids, oxyacids, are acids that have some amount of oxygen in the formula. Besides the hydrogen ion, the other part of this formula is the sulfate. So SO4 is the sulfate ion. And since that's an 8 ion, that becomes an ic acid. The only thing is this doesn't completely follow the pattern because it's not sulfic acid, it's sulfuric acid. So that's a little bit of an exception to the rule, I think. These two are also ic acids. Acetic acid comes from the ion acetate. So acetate changes to acetic and nitrate changes to nitric. So we know that acetic acid has the acetate ion as part of it. The acetate ion is C2H3O2 with a -1 charge. We're going to combine that with one hydrogen that has a +1 charge. And the formula we come up with here is HC2H3O2. So the nitrate ion is NO3 with a -1 charge. We're going to have to combine that with one hydrogen with a +1 charge, and that would give us a formula for nitric acid as HNO3. So this particular acid, HNO2 instead of HNO3, the NO2 ion is the nitrite ion, and the ite acids change to an us ending instead of an ic ending. So nitrite becomes nitrous acid, whereas nitrate became nitric acid. So if that pattern helps you remember the names, whatever is helpful, you can go ahead and use it. Maybe the acids that you have, there's not too many of them. It might just be easier to learn them. So whichever way works for you would be good. All right, let's just take a moment to summarize what we've learned about chemical nomenclature, naming compounds, either getting the name from the formula or getting the formula from the name. For either one, I wanted to point out that the first step is figuring out whether it is an ionic compound or a covalent compound, because they have slightly different rules for how to name them. So that's the first thing that you have to do. So if you have the formula and you see the formula and you see that it is a covalent molecular compound, then you would skip all this stuff and just go to step 6 and use the prefixes that we were just talking about at the beginning of this lecture. All right, I'm not sure why I've labeled this table 2.10. It must be a cut and paste error, but the table at the top of page 51 here is the table that we're talking about. And then if the first atom is here, you don't have to use the prefix mono. I think for a lot of people, doing step 6 is not a problem. The problem is that you want to skip to step 6 even if you have an ionic compound, and you can't. If it's an ionic compound, then you have to continue down the list to step 2 and figure out whether your metal is predictable or variable. If it's predictable, the cation, the metal, is just named as the element, and then you have to name the anion. If it's a variable charge, you need to figure out what Roman numeral is going to go in the parentheses. And so you have to figure out the charge on the variable charge cation and use the anion to do that. Okay. If you have the name and you are trying to get the formula and you know that it's a covalent compound, all nonmetals, then the prefixes that are written in the name will tell you exactly what to put in the formula. If it is not covalent, if it's ionic, then I think it's helpful to write the cation with the charge and the anion with the charge. Then you can use those charges to figure out how many of each element go into the formula. If you happen to have a polyatomic ion and you need more than one, you're going to need to put parentheses before you put the subscript to show that you have more than one of that whole polyatomic piece. So let's see if we could just practice a few more examples of naming with some of these things all mixed together, ionic or covalent. Then if it's ionic, we're going to figure out whether the cation is predictable or variable, and we're going to try to name the compound. So go ahead and pause here and see if you can try some of these examples before I continue. So let's go down these columns first and use that information to help us come up with the proper name of the compound. So this over here, we have a metal and a nonmetal. This is ionic. There are no metals here. There's nothing here that could be a cation. All nonmetals would make it a covalent or molecular compound. This one we have a metal and a polyatomic, that's ionic. This one we have a metal and a nonmetal, which is ionic. Also a metal and a nonmetal, so that's ionic. Here we have a metal and a polyatomic, so that's ionic. So this one is a little tricky. It looks like all nonmetals. We have nitrogen, hydrogen, and chlorine. None of these are metals. However, we do have one thing that can be a cation. This is our one polyatomic cation that we have. So this is a cation, a polyatomic cation, and then this nonmetal is the anion, so this is also an ionic compound. If it's ionic, which most of them are, we'll figure out whether it's a predictable or variable metal. We have a variable, a predictable, another predictable, variable, and predictable. This one is not really a metal cation. This is a polyatomic. So if you want to call this predictable, you can, because the charge on NH4 is known. NH4 ammonium has a +1 charge. This is called ammonium. I suppose this one is more like predictable because we definitely do not need a Roman numeral. We just need the name of the cation and the name of the anion. So let's go ahead and do this one first. Ammonium is the cation and chloride is the anion. Let's go ahead and do these other predictable ones next. We just have to name the cation and name the anion. So the cation is magnesium. The anion here is sulfite. Be careful, this is not sulfate, this is sulfite. So we have magnesium sulfite. This one is calcium bromide. And this one is potassium permanganate. Permanganate is another one of our polyatomic ions. Okay, so for these variable ones, we are going to need Roman numerals. Let's go ahead and leave space for them. So we have iron, and we're going to need a Roman numeral, and then we have chloride. This one we have tin, and we're going to need a Roman numeral, and we have oxide. All right, so we have two oxide ions, each with a -2. So altogether we have -4 as our negative charge. So we are going to need +4 as our positive charge. That means we have tin with a +4 charge. This is tin 4 oxide. And then here we have chloride with a -1 charge. We have 3 of them, so altogether we have -3, which means that altogether we have +3 in this compound. And since we only have one iron, it must be iron 3 in order to balance out the 3 chloride ions that we have. So one note that I've been asked about before is the oxide. We do have a polyatomic ion that is O2 with a -2 charge altogether, rather than 2 oxides adding up to -4. That peroxide polyatomic ion. You'll notice that when I saw these 2 oxygens together down here in the tin 4 oxide, I counted them as 2 oxide ions, rather than counting it as our peroxide polyatomic ion. So the peroxide polyatomic ion is more common in organic chemistry, organic compounds. So this is pretty rare in inorganic ionic compounds. So it is in our list of polyatomic ions that we should be familiar with. So if you see an ionic compound with 2 oxygens in them, like this SnO2, then just go ahead and count them as 2 oxide ions rather than a peroxide ion. Since I brought up the topic, I decided to show you some possible ionic peroxides that you could come across. Fortunately, the only ones that are known involve metals that have a predictable charge. And so it is kind of easy to tell that the 2 oxygens have altogether a charge of -2 together. So lithium peroxide, if you saw this formula, you would know that it's not just lithium oxide, because lithium oxide would have a total of a -4 charge. And so that would not be balanced with just 2 lithiums. So if you see this formula, again, this class we won't, but if you do see this formula with Li2O2, you know that it's lithium peroxide with O2 with a negative charge, because regular lithium oxide would have this formula, 2 +1 lithiums counterbalanced by 1 -2 charged oxygen ion, which is the much more normal compound to see. The most common peroxide that you would come across is hydrogen peroxide. I think we've mentioned this in class before, H2O2. It's used as a disinfectant. You can buy it in a first aid kit or in a pharmacy to use as an antiseptic. Let me just draw the Lewis structures of these 2 molecules here, just to emphasize that these are not ions that we're talking about, but since there are 2 oxygens together, we are talking about this as hydrogen peroxide, whereas this one we would just call water. I just kind of put this here as a little bit of a joke, a nod to our naming rules over here. So let's go ahead and just look at a couple of examples of these drawn out as ions, maybe the first and last one. The normal oxide ion has a -2 charge, so 1 oxide would balance with 1 barium, 1 oxide would balance with 2 lithium, so that is normally what we would see. If we do have the peroxide ion, then 2 lithiums would balance with 1 peroxide polyatomic ion. So this is the peroxide, this is the oxide. Let's go ahead and do barium. 1 barium and 1 peroxide ion. But again, these are not very common. You're not going to see these formulas very much compared to how often you will see these.